Okay, that'll start this time. I don't have your exams graded yet. I'm halfway done. But I'll get them done soonish. Hopefully by the next class. So the few things, we only have 2 weeks of lecture left. So we've got today, Wednesday, and the next week's Monday and Wednesday. And that's it. After that is finals. Our final is going to be 2 weeks from today. It'll be the same time, Monday at 12:30, and it'll be just like a midterm. It's just going to take the whole class period. And the final will be more cumulative than the last exam will be. So there will be questions you'll see dedicated to significant figures, things like that. But I would say maybe a third of it, well, yeah, just about a third is going to be new material. But like what new material? This is the stuff we're going to go over these next 2 weeks. So we're going to go over covalent bonding. I mean, pretty much that's it. Everything to do with covalent bonding. And it's quite a bit, because Lewis structure is a big part of it. Understanding the shapes of molecules, dipole moments, all that stuff. We're going to get through all of that. And we'll finish up with molecular orbital theory. That won't be heavily emphasized on the final because we're going to cover it again in 222. But we need the introduction at least so that it kind of all makes sense when we're switching gears at some point eventually. What else can I say? I think that's it. Any questions about kind of what we're going to be doing? I don't think it's super surprising. FYI, if you didn't see that email that I just sent out this morning, I failed to realize that the homework wasn't the same pace as the lecture, so the homework is a little bit more advanced. We haven't covered any of the stuff that's in the homework that was due today. So if you've done it already, I mean you're better off, but I will accept it next week. And I think that I looked. I think that's the last homework, the last week homework. So it's just next week, and then there's mastering chemistry. Actually, I haven't checked to see how well that's doing, but there is one every Monday still. I think even finals week there's one on Monday. But don't forget, if you've been doing mastering chemistry the whole time, I'm only going to grade out of a total of 260 points. So if you've done all the mastering chemistry up to this point, you probably have enough points. So do it just for practice at this point, because you get the full credit for that anyway. And if you haven't done the homework, start doing some homework, get some points so that you don't lose too many points from the homework grade. Okay, so let's get started. So we're going to go over covalent bonding. And this is kind of the opposite to what we've done so far. We've kind of covered ionic bonding without really saying it's ionic bonding. We have talked about Coulomb's law. And Coulomb's law describes how two charged particles attract each other. We've only looked at it as an electron attracted to the nucleus. But ionic bonding works the same way. It's a cation attracted to an anion, a negatively charged ion to a positively charged ion. And that's the simplest of all kinds of bonding. You just get an attraction from that. Covalent bonding is a little bit different. With covalent bonding, there is a little more subtlety in how the two atoms interact with each other to stay bonded together. So this is kind of a picture that will hopefully you recognize. What we're seeing here is a fluorine atom and a hydrogen atom, and these are their core charge models. So kind of like the shell model, but just the valence shell shown only with the core charge. And when they make a bond, and they make this covalent bond between the H and the F, this is the kind of picture you're going to end up with, where the electrons are being shared. So the one electron that comes from hydrogen is being shared with one of the electrons from the fluorine to complete what hopefully you recognize as, well, hey, now this fluorine kind of looks like a noble gas. It has 8 electrons in its second shell, looks like neon. Hydrogen has 2 electrons in the first shell. That's like helium. That's unique to hydrogen. And that's kind of what we're going to be seeing with covalent bonding in Lewis structures. So we need to start drawing these atoms a little bit more simply, because drawing these core charge models is going to get tedious. And so we've got a very shortcut way of drawing them. This is called a Lewis structure. And so with the Lewis structure, you just draw or write the symbol for the element, and then you show the valence electrons around it. We tend to group them, just to make it even easier, we tend to group them in clusters of 4. So top, bottom, left, and right. There's no difference. So whether you draw the lone electron that is the odd one out here, or up or down, doesn't matter. So this is a Lewis structure for fluorine. That is a Lewis structure for hydrogen. And when we draw them together, the 2 electrons that are shared between the 2 atoms are the ones that are between them. That's these 2 electrons are being shared between hydrogen and fluorine. In this particular case, one came from the hydrogen, one of these electrons came from the fluorine, but that's not a hard, fast rule. We'll see eventually covalent bonds where both electrons came from one atom and none electrons came from the other. It doesn't exactly matter where the electrons came from. What matters is they're sharing electrons between them. Okay? Now, that's even more complicated than we need to draw. Instead of showing a pair of electrons between the 2 atoms, what's more commonly shown is to draw a line between them, a bond. that is the bond. That is the representation of these 2 shared electrons between the 2 atoms, and it's a lot more clear. Those are the electrons being shared. So every time you see a line, this represents 2 electrons being shared between those 2 atoms. And so here's water. Water is the oxygen originally had 6 electrons in its valence shell, and it needs 2 more to have that noble gas-like electron configuration. And I'm going to call that an octet. It wants to have that octet meaning 8 electrons. So everything really likes to have this noble gas-like electron configuration, except for hydrogen, which doesn't want 8. Hydrogen just wants 2, because that's the noble gas electron configuration for helium. All right, so these are Lewis structures. You can see other variations. So let's just kind of turn to Chem Activity 12, page 221. We're just going to give a quick introduction to this. We're going to get a much more advanced look at this in the lab on Wednesday. Chem Activity down and switch to it. thing I forgot to mention is with Lewis structures, put the electrons around it, similar to how we would do Hund's rule. So remember, you put one electron in each spot before you pair them up. It's not super required, but it helps to kind of understand. It's actually better. Let's put that. We'll get to it. You might be thinking, well, wait a minute, isn't there S and P? Don't they have different energies? All that will become clear. They actually, we'll see. It gets complicated. That's how this class works. It just gets more complicated. Okay, I think let's talk about some of these answers real quick. Hopefully one was not difficult because one, you don't even have to look at the periodic table. If you know now that these Lewis structures show the valence electrons, then the shortcut is, well, if I know the valence electrons, it's the same as the core charge. For any neutral atom, the valence electrons is the same as the core charge. So this has one valence electron, it has a +1 core charge. This has 7 valence electrons, this is +7, 2 +2 core charge. Okay? You can calculate it yourself, you can look at the periodic table, that works too, but this is what kind of the language you're going to be speaking for like the next 2 weeks, is using Lewis structures for a lot of things. Being able to draw them yourself is important, so iodine, you have to go in the periodic table, know it's in group 7A, and draw 7 electrons around it. So, like I said, where you put that single electron doesn't matter, as long as it's in one of the locations, okay? Sulfur, and I kind of mentioned Hund's rule is kind of it's not exactly what we would use here, but when you're drawing electrons, 6 electrons, you're going to want to do 1, 2, 3, 4, 5, 6. And whether the 2 electrons are near each other or opposite sides, it doesn't matter. But there's going to be 2 unpaired electrons here. Not the same unpaired electrons we think of when we draw the orbital diagram, excuse me. But this is important to kind of keep in mind when we draw it this way, because one thing it tells you, hey, there's definitely not 8 electrons around here. So that's where we get to the next question. So this next question is for people that really haven't seen these before, just to kind of get used to what you can tell, what kind of knowledge that gives you. So in the first column, number of electrons surrounding each hydrogen atom in the molecule. So I guess we need to have a picture of what this looks like. I don't want to keep flipping back and forth. So HF looks like this. Draw it a little more darker. H2O looks like this. And NH3 looks like this. Or something like that. You're going to see that there's a couple ways to draw these. I mean, they're all going to have the same connections, but you could draw them turned around, doesn't matter. So number of electrons surrounding each hydrogen atom in the molecule. So did it draw like this, or did I use these bonds? Oh, they used, well, a combination. It's either bonds or electrons. So that's okay. So this bond here represents a pair of electrons. This pair of electrons is considered to be both next to the fluorine and next to the hydrogen. So when we talk about what's surrounding this hydrogen, there's a pair of electrons, that's it too. So in every single one of these molecules, if you look at what's next to a hydrogen, it's just 2 electrons, and that's it. If you look at the number of electrons surrounding the central atom, the other atom, so for fluorine, 2, 4, 6, and then the 2 here, 8. For the oxygen, 2, 4, 6, and 8. For the nitrogen, 2, 4, 6, 8. Everything, every other element besides hydrogen, there's going to be a few other exceptions, but most of them have 8 electrons around them. So the total number of electrons shown in the Lewis structure. So in this one, there's just 8. And actually, in all of them, coincidentally, there's just 8. 2, 4, 6, 8, 2, 4, 6, 8. The total number of valence electrons from hydrogen atoms in the molecule. So each hydrogen atom, if you think about how many valence electrons it comes with 1. So for each hydrogen atom, you're going to add 1 electron. So for H2O, there's 2 hydrogens, so 1 each. There's two valence electrons, 1 from each hydrogen. There's 3 in ammonia. And then we look at the number of valence electrons from the central or the other atom. Fluorine comes with 7. And then oxygen comes with 6. So when we look at this information, we go down to the bottom here. Here are 2 rules for Lewis structures. Hydrogens must have 2 electrons, and only 2. They can't have more. Any idea why they can't have more than 2 electrons?
Because they only have 1 shell.
They only have the first shell, and the first shell can hold 2 electrons max. That's it. If somehow you were to force the hydrogen to have a 3rd electron, it would have to go into a much higher energy shell, which it doesn't currently have. So hydrogen just takes 2, and that's it. And this is cut off in here, so I'll read it. The sum, well, that's fine. The sum of the shared bonding electrons and the lone pair electrons for carbon, nitrogen, oxygen, and fluorine must be 8. That is, the total number of electrons surrounding these atoms must be 8. This requirement is known as the octet rule. Usually the other elements in groups 14, 15, and 16, and 17 also follow the octet rule. So what we're basically saying is, for anything that is not a hydrogen, for the most part, or any nonmetal, I should say, that is hydrogen, they're going to need 8 electrons around it in order to be stable, in order to make a normally existing molecule that we could find in nature, okay? Yes, we could make all sorts of weird things too, but things that are stable, things that exist normally, all have this octet. All right, now here, this one. 8 electrons around that other non-hydrogen atom. Now we're only dealing with nonmetals here, because for a covalent bond, you generally have to have just nonmetals. The reason for that is if I suddenly introduce a metal, well, we know that metals like to lose their electrons. They tend to make cations. Nonmetals like to gain electrons. They tend to make anions. If you throw in a metal, you'll probably make an ionic bond instead. So all of these covalent bonds we're looking at, they're all between nonmetals. So hydrogen likes to have 2 electrons around it. Most other nonmetals like to have 8. And then we refer to this as the octet rule. Okay? Okay, so that's the beginning of covalent bonds. Let me actually make sure I've got this pointed right to that again. There we go. Oop, wrong one. Okay. So, how does the covalent bond form? Like, if we look at what we've just gone over, orbitals, what do they do? Well, let's start with just kind of the basics. In order for 2 atoms to share electrons, well, where do the electrons exist? The electrons are found inside an orbital. Right? The orbital is that volume of space around the nucleus where you're most likely to find the electron. So if one atom is going to share its electrons with another atom, then the orbitals have to overlap. The orbitals on both atoms have to overlap a little bit. And so the bonds are going to be a little bit shorter than kind of the ionic bonds we saw before. Although we didn't really see much of this. So there is a sweet spot, kind of. They will get close, but they don't get like infinitely close. The nuclei won't overlap. And that's because the nuclei of the 2 atoms, they're both positively charged. 2 positively charged particles will repel. Same goes for electrons. Electrons repel. But there is this interaction between the nucleus of one atom and the electrons of the other atom. That's where the attraction comes in. And the other one as well. The nucleus of this with the electrons from this atom. And there's this, there's sweet spot where the electrons and the repulsions balance out. Sorry, the electron attractions and the repulsions balance out. So let me find that real quick. It's in here.
A covalent bond consists of a pair of electrons shared by a pair of nuclei. Let's use this graph of potential energy versus the distance between the nuclei to see the change in energy as the distance decreases. We'll pay most attention to the bond in H2 and then look at Cl2 and larger halogens, defining 2 key bond parameters along the way. When the H atoms are far away from each other, we designate the energy as 0. As they move closer together, they attract each other more and more, and the energy decreases to a minimum. At this point, a stable hydrogen molecule has formed. If the nuclei come any closer, the energy increases rapidly as nuclear and electron repulsions take over. Now let's zoom in closer to see the overlapping atoms in more detail. When the atoms are far apart, they do not feel each other. But as they come closer, the nucleus of one atom attracts the electron cloud of the other, and the attraction draws the atoms still closer. Note the increasing electron density between them. Soon, the electron clouds interpenetrate. Attractions dominate, but repulsions between nuclei and between electrons become stronger. At the point of lowest energy, attractions just balance repulsions, and the 2 H atoms exist as an H2 molecule. The covalent bond is the mutual attraction between the nuclei and the electron pair. If the nuclei were to move closer, repulsions would outweigh attractions. The increase in potential energy would destabilize the system and the atoms would move apart again. In reality, the molecule vibrates, the atoms moving slightly farther and closer at the point of minimum energy. The bond length is the average distance. For H2, it is 74 picometers. The bond energy, the difference between the minimum energy and the starting point, is the energy needed to break a mole of H2 molecules into separate H atoms. For H2, it is 432 kilojoules.
So, really quickly, that vibration that they showed, where the atoms are kind of bouncing back and forth, that is the classical way of thinking about particles, right? Like, if we had a spring, we can see the spring, stretch it, it elongates, and we let go, it'll vibrate. It's convenient to think of atoms this way, and many chemists do think of atoms doing this vibration, but in reality, this process is quantized, just like all the other energies we've looked at before. So even though they show, oh, you could have it anywhere here, it's also in stages. So where you could have this vibration, this vibration, this vibration, and that's it. You know, you can't have every one. That's advanced. Don't worry about that. We're not going to worry about that too much. I just wanted to keep that, make sure you think of, like we went over the quantum mechanical atom, we don't want to forget about it. That still is the situation. But we are thinking, we're going to go back to the simpler way of thinking about atoms. And again, this energy is the energy required to break that bond. If I wanted to bring those two atoms back to zero, basically they're not connected anymore, I put in 432 kilojoules of energy per mole.
Now let's compare H2 with Cl2 and other halogen molecules. The much larger chlorine atoms reach the energy minimum and form a Cl2 molecule at a greater internuclear distance. Because the Cl nuclei are farther apart, it takes less energy to separate the atoms, thus a greater bond length and a smaller bond energy. Moving down group 7A, bromine is larger still, so we would expect an even greater bond length and smaller bond energy. And iodine, the largest of these halogens, continues the trend to longer, weaker bonds. Stepping back, we see that in each case, mutual attractions draw the atoms together and they form a covalent bond of specific length and energy.
All right, so that's it. The covalent bond is pretty simple looking. There is an ideal distance they get, and we can't calculate it very easily, but you know, we were giving you the numbers. If you never need them, you can look them up. Again, this is basically a distance of one atom from another, and as they're really far apart, they really don't feel each other, so the energy between them is zero, the potential energy. There's no change in energy for those atoms. But as you bring the two atoms together that you're going to make a covalent bond with, the potential energy drops. All right? Remember that most things want to be in as low energy as possible, so they will form the bond. If there is a lower energy, when they get close together, they will form that bond because they'll exist at a lower energy state. And there is this ideal distance they'll get where they balance out the attractions between one nucleus and the electrons versus the repulsions between the two nuclei and the cloud of electrons with each other. So this is the perfect distance where the attractions and the repulsions balance out. If you try to get it too close together, then the repulsions will be too strong. So, there's yet another look at it. Notice these are all the same distance and energy, 74 picometers, minus 436 kilojoules. Same here. These are all for hydrogen. So from this chart, you can get the bond energy of a hydrogen-hydrogen bond. And you can get the bond length. So, if I were to ask you, when making this bond, is it working yet? Is it an exothermic process? Does it release energy? Or is it an endothermic process? Does it require energy to make the bond? So when you're making the bond, what happens to energy? Does it get released or does it get absorbed? Clifford. A or B? Okay. All right, we have one opinion though, that's okay. It's still split though. So the actual answer here is that it is an exothermic process when a covalent bond is formed. So exothermic means an energy has been released. You can think of exoskeleton. Exo is external. It's releasing that energy. How does this work? Well, when you form the bond, suddenly the energy drops. That's the energy of the molecule. So if the energy of the molecule drops, where does it lose that energy to? It loses it to the surroundings. Energy is released when you make bonds like this. Okay? So again, the total energy that is released is a combination of all of the attractions and the repulsions together. And overall, they balance out to this overall amount of energy that is released, okay? Okay. So here is a list, and we're going to do another conductivity thing, of different bond energies, along with what is known as a bond order, and you're going to kind of take a look at that yourself. So let's dive right into conductivity 13 on page 226 and answer questions 2 through 10. You're going to get familiar with these bond energies and what all this means and how to think about it. About 10 minutes for that. Switch over real quick. many electrons are shared between two lines. So notice there's only one line here. Here there's two lines. But this is representing two sets of electrons.
Okay.
So that bond order means, yeah, there's what we call the double bond.
Okay. Okay, so this one's right then, right?
Yes.
It's basically the same question here, so you see that that's the number of pairs, the bond order is the same as the number of pairs shared.
It is, exactly. Yeah, so each line represents a pair of electrons. Yep. Break there. Hopefully you've had some time to read through some of these questions, think about them. It's a lot different when you're answering them yourself than me telling it to you. But so going through these questions, we have number 2, 3, I think and 4 are all kind of shared. There are 3 different bond orders, 2 examples of each bond order. So you know, if you look here, that's the bond order. We've got 1, and then we've got 2, and we've got 3 down here. So what's kind of, hopefully you saw the pattern, anything with a bond order of 3 has this 3-line bond in it. And each line we know represents a pair of electrons. Each line represents 2 electrons. So there's like 6 electrons being shared between these 2 nitrogens. So that's the bond order. What is the relationship between bond order and number of electrons shared? So bond order basically, is the number of pairs of shared electrons. So a bond order of 3 for the nitrogen-nitrogen bond means there's 3 pairs of electrons being shared. A bond order of 2 for the carbon-carbon bond means there's 2 pairs of electrons being shared. And here the carbon-hydrogen bond is a bond order 1. There's only 1 pair of electrons being shared. The 3 bond orders correspond to designations of single, double, and triple. And what is that, how are that related to bond order? Well, those are the names we give these types of bonds. So anything that is 1 pair of electrons we call a single bond, conveniently represented by a single line. Anything that has 2 pairs of electrons is a double bond, conveniently represented by 2 lines. And then this is a triple bond. And that's it. That's for plain old covalent stuff that we're going to cover today. That's it. There's just a single, double, and triple. There are way more unique bonds that exist, but these are the common ones. Okay. So rank the types of bond designations in order of increasing bond energy. So we just need to kind of grab 3 similar bonds, but with different bond order. So I wouldn't include nitrogen-nitrogen because that's different from a carbon-carbon bond. So let's make them all carbon-carbon, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. And if you compare those, the only difference now is bond order. It goes from kind of a 376 low energy to a higher energy to a much, much, much higher energy at 962. So triple bonds have a much higher bond dissociation energy, bond energy. So bond energy, same thing as bond dissociation energy. Dissociation means to dissociate, to break them apart, which is what the bond energy is. You put that much energy in, you'll break the bond, okay? So we also call that bond strength. So bonds that have a higher bond energy are said to be stronger bonds. All right, so the more energy it takes to break it, the stronger that bond is. That should make sense. And then we got questions. This is almost the same table, isn't it? Yeah. No, it's different, sorry. Consider the series HF, HCl, HBr, HI. What is the bond order for each of these bonds in the series? Well, if you looked at that table that I scrolled past, it's all single bonds. What is the trend observed in bond energy? So now we're comparing everything that's a single bond, but we're looking at the halogens. HF, HI, Cl, HBr, HI. And you can see when I go with HF, it's a very, very high bond energy. And as I go down the group of the periodic table down to HI, it becomes a lot lower. So the bond energies kind of follow the position of the periodic table a little bit. All right, that's interesting. What else can we say about it? So what is the bond length? Is defined as the distance between the nuclei. Consider the size of fluorine, chlorine, bromine, and iodine. What trend would you predict in the HX bond length in this series? So we're just going by what we know. On the periodic table, we know that fluorine is the smallest of the halogens because it's only got 2 shells. Chlorine is bigger, it's got 3 shells of electrons, and then bromine is bigger, iodine is the biggest. So if I pair up hydrogen and iodine, because iodine is so big, and remember, how do we measure the bond length? Well, we're measuring from the center of the 2 atoms, okay? So if this thing is really big, and of course hydrogen is pretty small comparatively. All right, these would probably be overlapping, so I didn't draw it correctly. But you're measuring from center to center. If I compare HI versus HF, and F is tiny, I would expect the bond length between hydrogen and fluorine to be a lot shorter than for something like HI. So the bond length should increase as I go down the periodic table. Considering the series Cl2, Br2, I2, what is the bond order? What trend is observed? And then let's talk about size again. So these are all bond order 1 again. There they are. these three, Cl, Br, and I. And the energies, they go down again. As you go down the periodic table, from chlorine to bromine to iodine, the bond energies drop, just like they did with the hydrogen version of those halogens. HF, HCl, HBr. FF is not in here, but we maybe expect FF if we're thinking, according to the trend, to be a higher energy, maybe. That's a surprising one. That's why it's not in here. But what about size? Well, the same explanation applies. If I have two I's together, two iodine atoms are big by themselves. If I try to put them together, their center to center is still going to be large. So an I2 molecule is going to have a longer bond length than two Cl's, basically. All right, so this is a short bond. This is going to be a much longer bond, just based on how big the atoms are. All right. Okay. So which of the following statements appear to be true? And here's a kind of a nice tie-in. The longer the bond, the stronger, or the shorter the bond, the stronger? Which one's correct?
Shorter the bond, the stronger.
Yeah, so the shorter it is, the stronger it is, right? We kind of looked up here. We said that chlorine Cl2, two Cl's will make a shorter bond than iodine, but the shorter the bond is, the stronger the bond becomes, the higher the energy it is. And the same goes for the H version. So HI is going to be a longer bond, HF is going to be a shorter bond, but that shorter bond has the largest bond energy out of the group. So the shorter the bond, the stronger it tends to be. That's actually a good generality. Generalization, not generality. Generalization. Okay. And then number 9. So what is the range of bond energies for single bonds? What is the range for double bonds? What is the range of triple bonds? So this one, just kind of keep in mind, you don't have to memorize these numbers. But if we look at all of the single bonds, the smallest single bond energy is about this one, 243. Although we've seen it lower on the second table, but you know, it gets kind of low. But the highest it gets is, I think that, 552 over here for the CH. So it barely breaks 500, right? It's under 500 usually. Whereas the double bond, all the double bonds, everything bond order 2 here, 720, 804, 782, so 700 to 800 or so. And then triple bonds. These are the only triple bonds we have up here. They're over 900. Okay, so these are kind of some energies we should expect. All right, just kind of keep in mind how big these energies are in general. You don't have to, like I said, you don't have to memorize those ranges. Just be familiar with them. Let's put it that way. So the most important determinant of bond strength is bond order. If the bond orders are the same, the shorter the bond, the stronger the bond. So this is a statement, and we need to back it up somehow. So the thing we just did when we looked at these bond order energy ranges, they were no surprise. Single bonds were around 500 or below, pretty universally. The double bonds were around 700 to 800 universally, and the triple bonds were over 900 universally. So that's the first thing you should be looking at in terms of figuring out how strong a bond is, whether it is a single, double, or triple bond. After that, once you have categorized it, it's a double bond, or it's a single bond, then you can compare the elements that you're attaching together. So then you can look at, is it a hydrogen with a helium, or a hydrogen with an iodine? Is it a hydrogen with a fluorine? And you can kind of judge the strength after that. But what's more important than the element that's being connected is the bond order. How many electrons are being used to connect those two atoms. So bond order is the most important. That's kind of the takeaway here. All right. FYI, all these Lewis structures, we're going to learn how to draw them from scratch in lab. So maybe you already have experience with it, but we'll go over that in lab. So again, which one is the strongest? head you should know. This is reinforcing what we just learned. All right. So excellent. Everybody is on board, in sync. HF is the strongest bond. Why? Fluorine is the smallest halogen out of this group, and so it's going to make the shortest bond. And that's, if they're all single bonds, then we have to look at then the atoms and look at which makes the shortest bond. So HF makes the shortest bond. Which one of these is the longest bond? Oh, we didn't talk about this yet, did we? But let's think about first length, and then first think about energy. Which one's the, how does energy and bond length correlate? And once you know that, well, you know which one is the strongest and which one's the weakest, right? Okay. So okay, we have most people voting A. I'm glad nobody picked the middle one, as that would be an odd choice. But in this case, the answer is A. So the reason for that is, well, we know that this is the strongest bond. This has got the highest bond energy because it's a triple bond. And we've already learned that the stronger bonds tend to be the shorter bonds, whereas the weaker bonds tend to be the longer bonds. So if we want the longest bond, we want the weakest bond. And that'll be the single bond. But which one of these is easiest to break? Okay. All right, everybody's on board. I think this is, I'm glad this is easy. Good. Hopefully it's easy for everybody, even if you're not answering. So A is the easiest to break. It's got the lowest bond energy. It's the weakest. And I'm not going to put this one on, but the strongest bond is going to be C, right? It's going to be the opposite of the one that's easiest to break. Okay. And this, there's no clicker for this, but what is the bond order of each? It goes with this, the number of bonds you see. This is bond order 1, this is bond order 2, this is bond order 3. You might be asking, why do we have this insistence on using this term bond order when it's easier to say it's a single bond, it's a double bond, it's a triple bond? We'll eventually get into bond orders of fractions. There is such a thing as a 1.5 bond or a 1 1/3 bond or something like that. So we'll eventually do weird bond orders, and you can't draw a 1.5 bond like with a Lewis structure. You can't. How do you draw a half a bond with a line? You can't. It's not easy to do. Not at least a way that anybody would recognize it. Okay. So this bond order concept, we still need to know about it, even though it seems redundant to double, single, triple bonds. All right. Oh, I've got little things on here. Anyway, ignore that for a second. But this is something we've already figured out. The length of a bond is inversely proportional or related to the strength of a bond. And so here, this is oxygen that we breathe. This is peroxide. So oxygen that we breathe actually has a double bond between the two oxygens. It's got a bond length of 121 picometers. It's shorter than the bond between two oxygens and peroxide, which is the stuff you have in the brown bottles that you treat cuts with, or if you have a stronger version you can bleach your hair with. And notice that the bond energy, this is a much stronger bond because it's a double bond. This is a much weaker bond. And coincidentally, that's why it's so much more reactive. So peroxide will react with anything. I mean, when somebody broke into my car so many years ago, they got blood everywhere because they cut their hand on my window. And I had to clean all the blood out. Peroxide did it. It was awful, but that's what did it. It's crazy. It just makes the bread go away. It turns the iron in the blood back to something you can't see anymore. Anyway, here's another comparison. This is nitrogen gas, which we're also breathing. Most of the air we breathe is nitrogen gas. It doesn't do anything to us. It's a triple bond. It's a very strong bond. It's a very short bond. This is an azide. It's called hydrazine. And this is what's inside your airbags. So there's a little ampule of this stuff, little tiny, tiny, tiny glass capsule. And when you have an accident, there's a mechanism that breaks it open, and this thing reacts so quickly with whatever else is in there that it makes a little explosion and it blows up the airbag. That's how they work. That's how reactive this stuff is. This is what they use in rockets too. This is fuel. But it's because the bond length is so short, it's a much weaker bond. As a result, it's easy to break those two nitrogens in half and make things with it. And it's a much longer bond. Was that?
So short.
I mean not short, long. Sorry, long. Excuse me. Okay. So bond order is the number of bonds. It's the number of shared pair of electrons between those bonds too. This is a conclusion. As bond order increases, the bond length will decrease, and the bond energy increases. So make sure that these relationships straighten in your head at some point, at least by the final. Here's a nice little table, if you want, that just kind of summarizes everything. But you shouldn't have to memorize it. It should kind of make sense. A single bond is going to be a weaker bond than a double bond. The length part is kind of the one that's kind of new, maybe. But again, if you ever forget, just go back to this kind of concept of looking at the periodic table and understanding, what you're seeing when you make bonds between two fluorines versus two iodines. Anyway. So bond energy increases as you go to triple bonds. It's a little bit weird seeing the arrow go down, but that's what it means. It's increasing going that way. This is the data we just looked at. Okay. Let's see. This is some more data. So here's two hydrogens. The hydrogen bond has a bond order of 1. The carbon-oxygen bond in carbon dioxide has a bond order of 2. And then nitrogen has a bond order of 3. The bond energies, as you can see, this is well within what we expect. Less than 500, around 700, 800, over 900. The thing down here, there are lone pairs. So we're not actually showing them here, but for instance, here, these electrons here, these are not involved in bonding, and they have names too. So we call these bonding pairs, the ones that are involved in bonding. The ones that are not involved in bonding, they're called non-bonding pairs, but they're more well known as lone pairs of electrons. Lone pairs meaning they're just a pair of electrons doing nothing on that atom. Okay. All right, so what else can we do with this data? What else can we do? How else can we analyze some information and come up with some generalizations on bonding and how nonmetals react? So that's what we need to do. We need to be able to predict things. So let's turn to a new tool. And this tool is going to be called Average Valence Electron Energy. It's a mouthful. You can shorten it by AVEE. So this is somewhat related to stuff we've covered already. Right? It's related to ionization energy. Remember that ionization energy is the energy required to remove the easiest to remove electron, so the outermost one. And that's always going to be, the lowest energy one, or should I say the highest potential energy one. So the one with the lowest ionization energy, right? So for instance, for potassium, that's the ionization energy of potassium. For aluminum, that's the ionization energy of aluminum. What we're seeing here is a list of photoelectron spectra data. You've seen this before. This is all the peaks and all their energies. Well, we're going to calculate what's called an average valence electron energy. So we're going to look at the energies to remove all of the valence electrons. So not just the easiest to remove electron, like in this case the 3p, but for aluminum, the valence electrons includes the 3s electrons, right? So we'll take an average of those. And so I guess we're going to do phosphorus here in this example. Well, let's actually go straight to the worksheet. I think this will kind of help you get through it. So what we're going to do is chem activity 19. Let's get it all the way forward. And like I said, we're developing a new tool for kind of understanding covalent bonding and predicting reactivity. So page 274, page 275, questions 1 and 2. All the way there. There we go. So, hopefully you've seen enough. So this is, we're not calculating ABE yet, but we're getting close. So one valence electron of hydrogen, what is the average ionization energy? I mean, so you go back to the table, it's 1.31, that's the outermost electron, it's the only one. And the average is 1.31, there's only one electron. The next question was, what is the average energy of the valence electrons for helium, I think it was. How did they question that? What is the average ionization energy of the 2 electrons in helium? So the idea here is if you try to calculate an average, well, one electron is 2.37, the other electron is 2.37. So if I add those together, divide by 2, like the basic average you guys know, it's 2.37. Right? So the average is 2.37. Both electrons are 2.37, so the average is 2.37. Hopefully that's clear. And then the follow-up question to that is, which atom, hydrogen or helium, holds its valence electrons more tightly? So on average, helium holds it more tightly because the average valence electron energy is 2.37. Higher energy. So it takes more energy to remove those electrons, and so they're held on more tightly. All right, I think that's not a surprise. We've known this. We know this already. We're just thinking of it in a slightly different way. We're kind of like looking at all the electrons in the valence shell at once. But so far, it's not really any different than looking at one electron at a time. So 2, what is the electron configuration for beryllium? Hopefully you wrote that out. 1s2, 2s2, like that. What is the average ionization energy for the valence electrons in beryllium? So valence electrons, we're only looking for these 2 right here. Those are the valence electrons. So that would be the energies from shell 2s, or subshell 2s, 0.90. So one electron is 0.90. The other electron is also 0.90. If we divide that by 2 electrons, we get 0.90. All right, that's not a big surprise. It's not a hard calculation to do. Now, if we compare that with carbon, so carbon's electron configuration is 1s2, 2s2, 2p2, and examine table 1 underline the ionization energies for the valence electrons in C for carbon. So now we're looking at 2 different positions. Let me get this header here. We're looking at the 2s and the 2p. Both of these are valence subshells. Right? Both the s and the p hold valence electrons. So we're looking at electrons that are both have an energy of 1.72 and 1.09. Right? So there's 2 electrons here have an energy of 1.72, and these have energies of 1.09. Oh, sorry. So go back to the question. Is the average ionization energy for valence electrons in carbon greater than or less than that for beryllium? How can you understand that without calculating anything? So here's how we have to look at this. So the 2 electrons at this energy and the 2 electrons at this energy, if we average them together, we can calculate that average, but notice that they're all higher than beryllium's anyway. Both of these numbers are higher anyway. So whatever the average is, it's going to be higher than beryllium's energy. So I don't even have to do the calculation to know that this is higher. If I average all of these electrons' energies together, it's going to be higher regardless. Yeah, it's greater than. So understanding that the average valence electron energy for carbon is higher, which atom holds its valence electrons more tightly? Carbon does, because it's harder to remove any of the valence electrons on average than to remove an electron from beryllium. That should make sense. Beryllium is a metal. Metals generally have easier to remove electrons. Non-metals don't want to lose electrons, they want to gain them. All right, so far that makes sense, hopefully. I think we're gonna get to the real math next. We've answered this. So let's calculate now an average valence electron energy for real. And I think we're gonna do this with phosphorus. So what we would do is, just like we did for carbon, we would look up the energy to remove an electron from that particular subshell. Oh, and it's kind of a mess up. So let's actually look it up ourselves, and let's just calculate it ourselves. So for phosphorus, and let me just write it out from scratch like we did for carbon. The electron configurations, 1s2, 2s2, 2p6, 3s2, 3p3. So we only care about the valence shell, just that. So if I look up the energy of the 3s electron for phosphorus, that's the 3s column, even though you can't see it, it's 1.95. And then for the 3p, it's right next to it, 1.06. To calculate an average, we need to add up all the electrons and their energies and divide by the number of electrons. So there's 2 electrons in this 3s subshell. So 1 electron costs this much to remove it. The second electron costs that same amount to remove it. The third electron, now we're getting to the 3p electrons. There's 3 of them in there. It takes this much energy to remove the third, takes this much energy to remove the fourth one, takes this much energy to remove the fifth. Now I'm not removing them subsequently. I'm not doing the first, then the second, then the third. I'm just saying, if I remove that one, it costs this much. If I remove the other one, it costs this much. If I remove this one instead, it would cost this much. But now we divide by the total. There's 5 total electrons. And if I do that, let's see, 1.95 plus 1.95 plus 1.06 plus 1.06, divide by 5, I get 1.416. It's not a hard calculation to do. That is the average valence electron energy. So what does this mean? On average, if I pick any of the valence electrons from phosphorus, that's what it's going to cost on average. Yes, if I pick the 3s, this is what it'll cost. If I pick the 3p, this is what it will cost. But now I'm talking about randomly picking a valence electron from phosphorus and doing it a bunch of times. It'll cost this much. I think this is kilojoules per mole, right? Or maybe it's, make sure I got the units right. Megajoules, sorry. Megajoules, not kilojoules. So we're not looking at individual atoms anymore. We're looking at a big cluster of phosphorus, and on average, that's what it's going to cost to remove a single valence electron. All right, now why do we care about this? Yeah, there it is. I think my sig figs are not as good as theirs, but that's fine. It's close enough. There we go. So why do we care? Well, you've seen the Lewis structures. When we do the Lewis structure for phosphorus, phosphorus's Lewis structure shows 5 valence electrons. We're not making a distinction between the s and the p electrons in this case. And that's what this is doing. This is combining the s and the p electrons into just one big pool and kind of telling you how, on average, how easy is it to remove one of them. This is going to give us a lot of information. So we'll get to that, how that works. So here's the average valence electron energy for several elements. Here's the one for phosphorus that we just calculated. See, mine's better there. It's actually turns up closer to the chart. And we can kind of see some patterns here. So notice that the metals over down here are really low average valence electron energies. Whereas if we go up here, it gets higher. So let's just answer the following questions 3 through 5 on page 276. Just kind of make sense of all this. Using my eraser. talk about the answers. So hopefully this was familiar. So we're kind of pretending the subshells don't exist almost. Because we're combining, like, that's what that's doing is it's kind of combining the S and the P shells back together into one, and we're just looking at one energy now. So this is kind of the original shell model, all right? So if we use the shell model, or the concept of core charge to explain average valence electron energy of atoms across a period, and I forgot to see if these existed. Okay, they do. Lithium and fluorine. So why is lithium's AVEE lower than fluorine's? Well, this electron is being held on by +1 core charge. It's not very tightly held on. These electrons, on average, are being held on by a very large core charge. And so it's going to take a lot more energy to remove one of those valence electrons, whether it's an S or a P electron, from the S subshell or the P subshell, doesn't matter. So that's the first question, or question 3. 4 is going by groups. I think it was groups, up and down. So I picked group 1, lithium and potassium. You could pick anything as an example. And instead of looking at core charges, I looked for the shell model, because the shell model more explicitly looks at the distance that the electrons get. So the outermost shell for lithium is shell 2. That electron, they're both being held on by a +1 core charge. So that's not what's different here. What's different is the distance that valence electron is from the nucleus. This electron is in shell 2. This electron is in shell 4. And so it's further away. And because it's further away, it's not feeling the nucleus as much, and so it's going to be a little bit easier to remove. So it's got a lower average valence electron energy than lithium does. It doesn't matter, there's only one. You can still call it an average, because even there's one, but it applies in every single group. And it's not a perfect trend, so sometimes it's not, well, I guess it works pretty well in this chart. They kind of, oh, here it is. Here it doesn't work very well, but in general it goes from high to low as you go down a group, okay? Okay, hopefully that makes sense. So number 5 now, why is Na more likely to form Na plus than O is to form O plus? So we know this from other models. All right, we can use the shell model, we can use the core charge model to explain why. But if we just look at the average valence electron energy, O versus, which was Na, sorry? My memory sucks. Na, okay. This is telling me that on average, to remove one of the valence electrons, on average, it takes 1.89 megajoules of energy per mole. Whereas for sodium, on average, to remove a valence electron, it takes much, much less energy. So this is much easier to turn into Na plus than oxygen is. So, I mean, we know these through other models. We know this, but now we're kind of coming up with a new model, a new way of explaining the same idea. And the reason for that is, we'll get to it in a second. Well, I'm not going to turn the thing on for this, but which holds its valence electrons more tightly? The one with the highest average valence electron energy is going to hold the electrons more tightly. Right? Average valence electron energy, this is the combination of the ionization energies of all the valence electrons. Okay? So trend-wise, here, I'll turn it on for this one. What do you expect the periodic trend for average valence electron energy to be? I mean, you can see it in your little worksheet, but you can predict it. You should be able to just understand in your head what it should be without knowing the exact numbers. Okay. Excellent. Everybody is on the same page. It increases across the row, decreases down a column. Okay. So, some of the other trends we can get, if we kind of now include the concept of metals versus nonmetals. and we compare their average valence electron energies, it turns out metals tend to have less than 1.06 ADEE values. Non-metals tend to always be greater than 1.26, and semi-metals tend to be somewhere in the middle. Hence, they're semi-metals, not quite metals, not quite non-metals, somewhere in the middle. So this leads us to the next thing. So this is just one way of looking at data, AVE, okay? We're just looking at photoelectron spectroscopy data and combining the numbers we saw for the valence electrons. Now, there's this concept of electronegativity, and this was invented, I can't remember the year it was invented, but when this came out, this was such an awesome tool, an awesome way to think about what happens. Let's first define electronegativity. Right? It is defined as the ability of an atom to attract shared electrons. That's electronegativity. So when we look at a bond HF, we think of, well, here's a shared pair of electrons. Does the fluorine or the hydrogen attract those electrons more or less than the other? Is it equal sharing? Or does one kind of attract those electrons more? That's what electronegativity is. And this kind of idea of understanding where those shared electrons kind of tend to hang around helped explain a lot of things. So how do we get electronegativity? Well, it turns out that one of the ways to calculate electronegativity is through average valence electron energy. That's why we looked at it. If we multiply that number that we just calculated and all of the ones in that table, each of them by 1.8, we get approximately an electronegativity that works. I'll say this, the way that you calculate electronegativity, it differs. There's a lot of formulas people have come up with to generate a table. Electronegativity is not something you can measure directly. It is not. You can't just take a molecule and measure it. You have to calculate it through various means. One way is using average valence electron energy. There's other ways. So if you go online and you look up electronegativity, you're going to see a lot of different charts. The most common one is the one invented by Linus Pauling, who was a chemist, biochemist. He got the Nobel Prize twice. One for chemistry or biochemistry, I can't remember. One for science, one for the Peace Prize. But there's plenty other ones. I'll say this: the one that's in your workbooks in the back, that is not the standard one. You're going to use that one for any of the problems that the workbook tries to have you do. But I'm going to on the screen. I'm going to show you the common one. All right. So it's not, like I said, it's not a measured quantity. You have to calculate it, and one of the ways to calculate it is average valence electron energy. There are no units to it. So even though our average valence electron energy is megajoules per mole because it comes from real data, when we translate it into an electronegativity, we just drop the units. It's a unitless number. And like I said, there's many different tables. So this one says 15 or so. They all have their strengths and their weaknesses, okay? So what is the periodic trend for electronegativity? We know this already because we know the one for average valence electron energy. So it increases across a row, it decreases down a column. So here is the most common one. This is the Pauling one. And one of the key characteristics of the Pauling one is fluorine. First of all, the noble gases are not there. So why are the noble gases not there? Well, remember what the definition is. It's the ability of an element or an atom to attract shared electrons. Well, in order to do that, they need to be in a covalent bond. And noble gases don't really make covalent bonds. There's some exceptions, of course, but noble gases don't really make covalent bonds, so they're not included on this table. Fluorine is 4. It is the highest electronegativity. And since it's to the top right of the periodic table, it is the highest. Because as you go to the left and you go down, the electronegativity goes down. So you don't have to memorize any numbers other than maybe you remember that fluorine is 4, but you don't even have to do that. You just need to know that fluorine is the highest. But what is actually helpful is to remember where hydrogen's position really is. So even though we put hydrogen here because of the group 1 kind of thing, idea, 1 electron, 1 valence electron, the electronegativity of hydrogen belongs between boron and carbon. So hydrogen kind of belongs here in terms of electronegativity. So when you're thinking, when you're looking at a molecule, we're going to be comparing, hey, these two things are covalently bonded, what are their electronegativities? Just remember that carbon and hydrogen are close together. They're not the same, but they're close. That's probably the only thing you really have to memorize, just to get familiar. Other than that, we'll give you these tables to use, if you need to use the numbers. But again, if you don't need to use the numbers, you just need to know the trend. That you should know. You should know it goes higher as you go up to the right. Okay. And this is actually in your textbook, like the Mastering Chemistry version. Here is yet another view of it. And so here we're kind of sticking hydrogen where it belongs now. Kind of there somewhere. It's not a perfect trend. You can see that the transition metals are always a little bit funky. But in general, as you go left to right, you go up. And as you go top to bottom, it goes down. All right, let's not do well, we have 10 minutes left. Okay. Maybe we should just, let me see if the video works. If it works, we'll do that. Oh wait, no. Maybe I don't want to do that. Sorry about that.
Can this beanie hat protect my head from harmful 4G and 5G self?
Can't believe that made
Humans, like chemicals, are really all about bonds. Think about all the relationships in your life. You're a casual acquaintance to some people, a colleague or friend to others, and maybe more to that someone special. Maybe you're dating someone casually, or you're in a committed relationship, or you're married. There are all kinds of different combinations of people out there. And sometimes, people fall for a vampire or a werewolf. Who am I to judge? Fact is, each type of relationship requires different things from you and the other person. But if you play your cards right, these relationships allow you to relax and escape the stresses that come with the constant search for affection. Distance is important in relationships too. Of course, too much distance makes it hard to stay focused on each other and requires a lot of effort to keep things together. And I may not have to tell you, too little distance can be a problem as well. Everyone needs their space, and when you don't have any, you just end up pushing away from whatever's crowding you. In this way, atoms are a lot like us. We call their relationships bonds, just like we do with our own relationships. And there are many different types. Each kind of atomic relationship requires a different type of energy, but they all do best when they settle into the lowest stress situation possible. The nature of the bond between atoms is related to the distance between them, and like people and vampires and werewolves, I suppose, it also depends on how positive or negative they are. The difference is that unlike human relationships, we can analyze exactly what makes different kinds of chemical relationships work, and that's what this episode is all about. But people, please remember that we here at Crash Course do not dispense relationship advice. First things first, why do atoms do this at all? Well, like everything else in the universe, atoms do whatever they can to reduce their overall energy. And they reach their lowest energy by achieving a balance between attractive and repulsive forces, being neither too clingy nor too aloof. So when two atoms approach each other, the electrons of each are attracted to the protons of the other. This is the electrostatic force. Like charges repel, opposites attract. Like in real life, or at least Paula Abdul songs. I know, I'm old. So when one atom is attracted to another, just like Edward Cullen and Bella in chemistry class, to use a slightly more timely reference, it gets stressed out by the attractive force and tries to relieve the stress by getting closer. We've all been there, right? That hot, nerdy vampire girl in your chemistry class, it's intense. The pull is so strong that the stress level or energy rises when the two are separated, so they stay close. But sometimes they can get a little too close. When that happens, the nuclei repel each other because of their like charges, and the energy between them rapidly increases, and they both back off just enough to find that perfect little distance between them, and everyone relaxes. This ideal, wonderful distance is the bond length. It's the distance between two nuclei at the point of minimum energy. In other words, where the attractive and repulsive forces cancel each other out. The distance at which these two atoms of chlorine reach their minimum energy caught between the attraction of the electrons to the nucleus and the protons repelling the nuclei is the bond length. That energy minimum, which we know absolutely is negative 239 kilojoules per mole, occurs when the distance between the atoms is 0.00199 nanometers. That distance is the bond length of Cl2, chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. As you know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativity of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one, like how all of the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's going to happen. They're attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion.
Alright, he's going to keep going. But the section on electronegativity, that's the part that we're going to work on. And that whole polar bond thing, that's the key part. So, or is it? We don't have time for this, but yeah, there we go. A hydrogen and an oxygen. If we look up their electronegativities, hydrogen is 2.1, oxygen is 3.5. And the difference in electronegativity is different enough. So we're going to calculate differences. We're going to have a scale where we can say, oh, it's kind of nonpolar or it's very polar. This is very polar. There's a big difference. Oxygen is more attracted to the shared electrons. And so the shared electrons that would normally hang out between tend to hang out more often. Remember, electrons are, so even though we say they hang out here, we can't really say that exactly. It's a Heisenberg's uncertainty principle. They're more likely to be found between the two atoms. But if they're more attracted to the oxygen, they're less likely to be found here now, and more likely to be found around the oxygen only, even though there is a bond between them. Now you can take that to extreme. If the electronegativity difference is so great, so if we have a metal, for instance, and a non-metal, a metal has a really low electronegativity, and a non-metal like oxygen has a high electronegativity, then the shared electrons just don't want to hang around with the metal at all anymore. They just want to hang around with the oxygen. And that's where an ionic bond forms, where the electron just exists on the oxygen. The oxygen has a minus, or usually a 2- charge now. They've stolen the electrons from the metal, and the metal will have a positive charge. So we're going to come back to that on Wednesday. We'll have a big lab on Lewis structures, and then we'll continue this concept of covalent bonds and bonding theory, just kind of understanding how all this works, how we can use different bonding models to come up with shapes understand dipole moments, so this positive, negative charge they mentioned that a molecule can have. And we'll fit it all in the next 2 weeks, so. All right. Feel free to use these links in the video, in the slides and stuff to watch them yourself. There's plenty of good videos on the internet. Don't watch the ads are horrible. I can't believe that ad was on this video. That's like insane. It's such a bad match.
Yeah. How did you manage that? Because that usually it matches to you, right?
You know, am I logged in?
Are you?
I am logged in.
That is bizarre.
I don't know. Oh no, we're not here. I am logged into YouTube, so I don't know. I tend to turn off all of the analytics on my Google stuff, so it doesn't. That's supposed to track me as well.
Mine does too, so it's random stuff.
It's usually random, yeah.
I can't believe they aired the
Yeah.
conspiracy theory.
It's
What the
it's
hell?
the worst matchup ever. Yeah.
Well, we'll see if you're wearing a beanie on Wednesday. when we
Yeah,
find out.
yeah.
Was it a special meeting?
It was like it's probably a
Yeah,
copper line inside or something. I don't know.
Yeah, it looked like it was
like a
whole
To block those
conspiracy
5G signals.
Yeah,
theory.
like those makeshift parody box or whatever.
Sure, I've heard of it. I
Yeah.
didn't notice.
Like it causes
So-
COVID or some crap. And they're saying that this will
Uh,
protect you.
so don't.
Because it's a new and improved tool.
How did you
Oh,
fill this out already? Okay.
We'll buy it.
I had COVID and
So
I,
this
and I
we
was
haven't
really
covered
sick
this
and
at all. We're
and I
gonna cover
had
this in a
asthma.
while.
And
That's why I
my
say
daughter
it's
also,
next week, but
we didn't eat. And I was like, I wonder if.
yeah, this is
everyone
gonna
was
have
really
so
sick and
just
eat.
to kind of
And my,
give you quick,
and I was like,
uh,
they've studied like people's
this has
diets
1, 2, 3, 4
how
groups
sick
of
they
electrons
get
right
or
there.
where
You just look at what's connected.
Of course, it's a very simple.
So if there's lone pairs that count, so like this hydrogen has the lone pair 1, this bond 2, and this double bond 3. We just count the number of groups of electrons.
Is that
And so this has
phosphate?
4
This
groups,
is
and
like-
that's
yeah.
4 electron domains. means
Because
tetrahedral.
this makes it.
And tetrahedral, and so when you do perspective,
I didn't.
and this is what we're going to teach in the lab. You don't have to be an artist. So for flat things, it's
This
easy.
week's
So like
homework
trigonal planar.
was everything we just
It's 120-degree bond angles. Like that's
Okay.
Completed.
120. It's like you arrange it in a circle and it's 120-degree angles.
Okay.
But for 4 things, you can't do it flat. It's 3D. And the way we do 3D is you do one
The computer
up,
thing, sometimes
one
like
to the
it
side
didn't
that's
have that
in the
big
plane of the
little
board.
answer right
And then we use
wrong.
these
I think I would be
wedges.
checking my homework.
So solid wedge
You know what I mean?
in chemistry means perspective towards you coming out of
Thanks
the
for
page.
calling it that.
Yeah, no problem.
And the dashed wedge means perspective going away from you, going into the board.
Okay.
So that's how we do 3D without many artists. So that's the very common, that's tetrahedral.
Thank you.
And it doesn't matter if you have the wedges on this side or on this side, but that's the shape that you draw generally.
Okay.
So, I don't know, is it CL or H? CL, okay. So I would draw it like this.
Okay.
And, yeah, if you want to be an artist, you draw this bigger, you draw that smaller. You know.
And then I noticed that so the one with the less activity is usually the one in the center.
Yes, yeah, definitely. A shortcut to that is usually the first element listed is in the center, unless it's hydrogen, and then it's not.
Yeah, I noticed that one too.
Yeah, but yeah, the better one is yes, the less electronegative elements.
Okay.
And then another rule is organic molecules, meaning carbon-hydrogen bonds. You see that, generally you'll see a lot of carbons. So make a chain out of carbons and connect everything to the carbons afterwards.
Oh.
So if there's 2 carbons, draw the 2 carbons first, connect it to each other, and then draw what's left on them. And you gotta remember, you know, so we'll get to that on Wednesday, but like there's gonna be a whole lab worksheet we're gonna do that we're just gonna practice with each other.
Right. Yeah, it's starting to come all back. I learned this back in like high school.
Yeah, I mean,